Hi guys, Justin here from chemistrynotes.com, and this is the very first video for section 18. Section 18 is kind of like chapter 18, of course. I know I say it all the time. Section 18 is called Transition Metals and Coordination Chemistry. Now, coordination chemistry, we're going to basically start a little bit of it at like the 10-minute mark today, and then we'll gradually start to focus on that. But for the most part, this video will be, for some of you, a little bit of a review. We're going to talk about transition metals and the D block, and we're going to talk about some of their similarities across a period as well as down a group for transition metals. And we're going to describe some of the more popular transition metals and what their importances are. And it's just kind of a setup for some of the coordination, compound, complex ion, and coordination chemistry stuff that gets a little troublesome later on in the section. So let's just get started, all right? Section 18, transition metals and coordination chemistry. Transition metals are the D block metals, right? And we learned about D block metals and electron configurations in section 7. And they can be coordinated or bound to something called ligands. More on that later in the section. Just for now, transition metals can be coordinated or bound to ligands. 6 important transition metals. Iron, it's used for steel. It's in complexes of, complexes of iron provide transport and storage of O2 in living organisms. Copper, Cu, is an electrical wiring. So you can find it in water, pipes, and it's a very good conductor of electricity. Ag, silver, all right. Now, aside from the obvious, like jewelry, it's also found in photographic paper. Thought that would be an interesting point to write down here, so I included that. Zinc is found in 150, believe it or not. Zinc is found in 150 biomolecules found in humans. CO, that's big C, little o, right? It's not carbon monoxide, it's cobalt. Similar to zinc, it's present in essential biomolecules. The major one is vitamin B12. Some people refer to it as a coenzyme or a cofactor. We're not going to worry about those terms. So, those are just the 6 that I wanted to mention. Now, in this section, in other words, in section 18, okay, which is transition metals and coordination compounds. In this section, we're going to focus on properties of transition metals and the bonding, the structure, and other various properties of these D block elements, okay? So, I've underlined complex ions here, and I've underlined it twice. And we are going to get into complex ions in a ton of detail, not today, but later on. So right now I'm just kind of setting that up, okay? So it says, in this section, we're going to focus on properties of transition metals and the bonding, structure, and properties of the complex ions of these D block metals. So what are 5 general properties of transition metals? And again, this is probably a review from section 2. Section 2 in our course is atoms, molecules, and ions. Long time ago, right? Section 2, first semester. So number 1 of the 5 general properties of transition metals is, unlike other elements, transition metals show similar properties both down a group, like everybody else, but also across a period. So I've underlined across a period. That's kind of unique to transition metals. Now, why is that specifically? Well, they are called the D block elements, right? So that might be some sort of trigger phrase to think of. But the answer, it says, why? So why do transition metals not only show similar characteristics, chemical and physical properties down a group like everybody, but also across a period? And the answer to that is because across a period, transition metals add inner, as opposed to valence, they add inner core electrons to inner d and or f orbitals, which don't participate as easily as the s and p electrons do. The s and p electrons are the valence electrons. They're the outermost electrons, right? They participate in things like bonding, whereas the inner core electrons are kind of, they're hidden, right? That's why when we talked about the effective nuclear charge, ZEFF, it says, a little star there, all other types of elements add electrons to the outer s and or p orbitals across a period. If you remember the d, when you fill in the d orbitals, right, the d is 1 behind the period number, and the f is 2 behind your period number, right? So when you're adding extra electrons moving across a period, adding extra electrons to these inner core d orbitals, you're not really affecting the chemistry as much because you're not outing to the outermost valence electron shells. All right, number 2, transition metals are lustrous, okay? Fancy word for shiny. They're good conductors of electricity. Why are they good conductors of electricity? Because of the delocalized electron model for metallic bonding. All right, we talked about that in section 10, by the way. Liquid, solids, and intermolecular forces. Regarding conduction and good conductors of electricity, silver is the best conductor. Copper is a very close second, and copper is much cheaper, which is why we always think of copper as the best wire to have as far as conducting electricity. Silver is better, but it's just ridiculously expensive compared to copper. Number 4 of our 5 properties of transition metals. Number 4, top of a new page of notes here, it says, despite visible similarities, lustrous, shiny, etc., transition metals have varying chemical and physical properties. I'm just going to list an extreme here. As far as melting point and boiling point, right? Tungsten, atomic symbol W for tungsten. Tungsten is in light bulb filaments, right? It's that little thing you see going across, that little wire going across the old light bulbs. Tungsten melts at 3,400 degrees Celsius. 3,400 degrees Celsius. So 100% solid at room temperature, duh, right? But mercury, which is also lustrous and shiny looking, is a liquid at room temperature. It's a liquid at 25 degrees Celsius, okay? And B, another example, hardness. When we think of iron and titanium, we think of these as being very strong and sturdy. These are used in structures. But things like copper, silver, and gold are malleable and ductile. Malleable means you can actually hammer the metal into whatever shape you want. Okay, it can be hammered into thin sheets. Ductile means it can be drawn into a fine wire. Both of those, malleable and ductile, basically just means it's a soft metal. Not brittle, but soft. Why isn't it brittle? Again, because of the sea of electrons and the delocalized electron model that we mentioned on the prior page. Number 5, when forming ionic compounds, okay, we learned a lot about ionic compounds back in the first semester, right? When forming ionic compounds with nonmetals or polyatomic anions, transition metals exhibit typical characteristics. Now, by the way, transition metals often can have multiple charges, right? Copper can be a +1, it can also be a +2. Iron likes to be a +2 and a +3, for example. So it says when forming ionic compounds, transition metals exhibit typical characteristics. Often there's more than one oxidation state, right? More than one charge. And I gave you an example down there of iron being +2 or +3. That's kind of characteristic only to transition metals. Second, B, cations, right? That's the positive ion. Cations are often complex ions. Now we've kind of reached almost the 10-minute mark. This is where it might be a little bit new. Hopefully it's new. Cations are often complex ions. So what is a complex ion? Complex ions are species where the transition metal is surrounded by ligands. It's attached to things. Okay, what are these things? What are these things that you're referring to as ligands? I've never heard this term before. Ligands needs its own definition. And ligands are molecules, so they're neutral molecules or they're charged ions. They're molecules or ions that act as Lewis bases. And Lewis bases are just electron pair donators. Now here is a funny looking sketch I've just drawn as an example. This is a typical coordination compound. So you see I've got bracket CONH3,6. And on the outside, I got Cl3. So we'll talk all about the structure and the way this is written and its setup. But for right now, the entire thing is referred to as a coordination compound. And the one that we see there contains 3 chloride anions and just one, CONH3,6 3+ cation. Okay, that chunk of cation is a complex ion. The 6 NH3s that you see attached to cobalt are ligands. Okay, they're coordinated to the CO3+ metal center. You see how the CO is a 3+ charge and then the entire CONH3,6 is a 3+ charge? That, and we'll learn more on this later, I promise. That leads us to believe now, though, that the NH3 are neutral ligands. And what I'm drawing is an octahedral shape. If cobalt's going to have 6 attachments, right? We learned back when we did Lewis structures that 6 attachments are going to adopt an octahedral arrangement. And I put brackets around it. And remember, the dashes are going back and the wedges come out at us. All right, C. Most transition metal complexes, transition metal coordination compounds, are colored. Why is this? And we'll go into a lot of detail on this later on. But most compounds are colored because the transition metal ion in the complex ion, like cobalt we just saw in the previous example, because the transition metal ion in the complex ion absorbs visible light. And what do we see? We see the complementary color of what's getting absorbed. So I'm going to do this sketch, the same sketch I gave you in section 7, Viboger. Okay? If something absorbs violet light, it appears yellow. If something absorbs blue light, it appears orange. If something absorbs green light, it appears red. And then vice versa for all 3 of those sections. If something absorbs yellow light, it's going to appear violet. Okay? And then D, many transition metals are paramagnetic. Paramagnetic means it contains at least 1 unpaired electron. So if I'm talking about unpaired electrons, maybe I'm going to have to go over the way that we draw electron configurations. And that is the subject of our next video, which is coming up. That will be section 18, video number 2. We'll start off by doing the diagonal roll. Remember that from section 7. And we'll talk about electron configurations. And then I promise we'll move into some new stuff on coordination compounds, complex ions, ligands, types of ligands, etc. So you want to stick around for that. It's coming up next. Thank you.